Okay, let's move forward with the presentation. So today's topic is about additive manufacturing quality control. So what we are looking at is how do we holistically okay, how can we basically look at the quality related issues with additive manufacturing in a holistic manner. The reason why I say holistic manner is because with additive manufacturing, there are multiple steps that are involved, starting from powder to loading the part to printing, heat treatment, post-processing, before the part is actually measured. And when we measure the part in the final stage, there might be some porosity, there might be some cracks, or there might be deformations, or part is out of tolerance, or surface quality is not of desired to desired specifications. In that case, what we need to understand is where exactly is that defect coming from. And in order to understand what is the origin of defect and be able to produce produce a part which is defect free, we need to understand what mitigation steps one needs to take in order to get the part right the first time. And for this reason, what we have understood and what we have implemented is a holistic quality control, starting from powder all the way to the finished parts. And this is what we call our blue line. Next slide. Yeah. So when I say blue line, basically it's like what we start looking at is quality analysis on the powder section. That can be done using SEM light microscopy or CT. And for each of these techniques, what we are doing is collecting data. And the idea is be able to inform the entire process. So data collected here, where we have a powder of certain specifications, if that can be used or not used, pass or fail, or if we do have a powder of certain different specifications, can we use our print parameters in order to get a better part out of out of that batch of powder? In order to be able to do this type of analysis, what we need is this data to be integrated. So we analyze the powder. We also have in situ monitoring process where we are looking at the part as that is being built. I just got a comment saying I'm not able to see the PPT in full screen. Okay, I'm showing the presentation in a full screen. So if there
Yeah,
are,
I'm not sure what the problem is. I'm seeing it in full screen as well.
okay, so we'll proceed. The recording of the video will be also available in case something, if it is not rendering very well on your screen. At the end of presentation, Jason is going to send out a link with the recording of this presentation. So the idea is basically be able to monitor different aspects of the process. So you're monitoring the powder while the part is inside, while the powder is inside the printer and part is getting created. Once the part comes out of printer, depowdering and post heat treatment, then we can start getting into material science aspect as well, where we start looking at defect and mechanical properties like grain structure or inclusions. Then we go into also measuring surface finish as well as dimensional tolerances. And at the end of the day, you have a data analytics software, which is basically collecting all the data and informing process of what if there is some telltale signals of part not having a desired properties, and how do you go and mitigate that step. So let's start off with one example on where we are using this whole integrated process to understand what benefits it can bring to additive manufacturing. So the idea is additive manufacturing currently has a lot of issues related to quality and reproducibility, especially in metals. And as we start going more towards production stage, all these problems need to be mitigated before we can actually call a production ready for each application. For some applications, it's already a production ready system. For other application, the time it takes from the prototyping, from the concept to prototyping to production stage could be very, very long, could be up like anywhere from 12 months to about 24 months. And what we want to be able to do is by doing the holistic analysis, can you reduce that time from number of months to just few weeks? And I'll show you an example. So this was a case study that we did for the Air Force Sustainment project. And this is a heat exchanger that designed. So here is the background on the project. So a few years ago, there was an article in Wired magazine talking about how can you keep these old planes in service all the way to 2050, because that's what Air Force Sustainment Program wants to do, especially when the manufacturing bases have been either closed or moved out, because these are fairly old aircraft. At the same time, making one-off parts is extremely expensive. Few years later, on the same Wired magazine article, part came in, another article showed about saying, we can have the replacement parts or tools printed with 3D manufacturing in absence of manufacturing bases not existing here. And that can keep this aging fleet operational till 2050. And the part I'm going to show you is actually one of the demo pieces for this program. So this, what we're looking at is a fuel-cooled oil cooler. It's a heat exchanger. And the most difficult part about this part was the replacement cost of this part is too high and long lead times, especially because the manufacturing of this part in traditional manner would take a long time. And since the replacement volumes required are fairly low in number, nobody would basically set up a different manufacturing process for this. And additive manufacturing works quite well because part is complex to make and we require them in lower volumes. So what this part actually achieves is basically you have a cold fuel coming in from wings, exchanges heat with the hot lubricant, and both the fluids are maintained at optimum temperature. So the part has to be a functional part as well, not just a demonstration piece on something can be printed, but this part would actually fly on the planes. The simulations were performed on this geometry that was created to be manufactured using additive manufacturing. And you can look at the amount of, from simulations, you can look at what type of pressure drops you can get, what different type of heat temperatures you're going to be able to maintain in different areas. One thing that I wanted to point out about this is if the part is not manufactured correctly, then what would happen is the pressure drop in different areas would be different. If the surface roughness is not accounted for very well, then you might have a very different area or much greater area available for surface exchange, for heat exchange, if surfaces are fairly rough versus if the surfaces are fairly coarse. So once you start accounting for the amount of area available for heat exchange, most of the simulations get thrown out of window because they're not practical anymore. And if you think about most of the functional surfaces are hidden inside the part, they're not available for easy surface treatment procedures. So surface treatment sometimes can become expensive as well. So in order to understand how can we look at the defects and surface roughnesses as well. So that was one of the key challenges going forward with this program besides reproducibility. So this part was created with the aluminum, silicon, and magnesium. This part was created in UDRI in partnership with AFRL on, I think, concept laser machine. And once the part was created, the part was sent to our lab. We have ZEISS has a integrated quality control lab based inside Oak Ridge National Lab, specifically focusing on metal additive manufacturing. So I'll just show you some of the measurements that we did on this part. So the part was first measured using CMM, and after CMM, the same part was again scanned to get much denser quality data at slightly coarser resolution using 3D scanner. 3D scanner is of course going to give you much faster data, but cannot show you internal defects. In order to get the internal defects, we scan the same part with the CT system, where we can look at not only the surface internal defects, as well as we can also do metrology using CT data, because this system is called Metrotome. It's designed for metrology and tomography together. Then once having identified large defects, if you want to understand what is some of the features which are at lower resolution not being captured by CT, we use micro CT to be able to show that image, the same part without cutting it open. So you're looking at the whole part, but you're able to show much smaller size pores. And after having seen small size pores, if you want to understand about surface roughness, we have different solutions available. So one of the solutions I'm showing you here is confocal optical microscopy. We have laser confocal, and X-ray CT also is used for measuring surface roughness, but on the inside where the light or a probe cannot touch it. And then we also used SEM in order to understand the chemistry as well as grain structure of this part. And after having shown all the measurement side of it, I can now walk you through the results that we got using all this equipment. So the part was measured, and what we're now seeing is just the surface of the part. And very first thing that we can do is compare nominal to actual and look at the deformation on the surface. So anything purple is showing the part is deforming out of spec. Anything green basically shows the part is in spec. So that's automatically your very first quality data that's coming in. Using CT, you can also go and do metrology on the internal part. So you can measure diameter of every single tube, thickness of every single baffle, angles, orientation. You could go and measure pretty much anything you like. But CT also gives you defects. So you can start seeing the porosity in these parts. But sometimes that image is not sufficient. You can image the same part at higher resolution and starts revealing more defects. As you start imaging it even higher resolution, even smaller pores starts becoming visible. And then you can add SEM basically to get to even sub-nanometer resolution imaging. So you can keep on adding details to the image without having to lose the orientation. So this is the power of this multi-resolution imaging. And what if we are able to do is not only show where the pores exist, but how can we go back and identify what caused the pores if the pores are of certain resolution? Because just doing CT alone is going to give you an A answer, but that's not the final answer, because the coarser resolution CT, which allows you to see the entire part, might be very coarse in resolution, so it not be able to pick up small pores. On the other hand, if you go with optical microscopy or SEM directly, where we are able to see only the finest of the pores, you are limited to basically collecting data from a very small region, and region may not be representative. So by combining all these different approaches, what we are able to show is you're able to see the entire part, identify the region which are representative but are not being able to captured by the coarser resolution, and then use a higher resolution instrument to go in a pointed direction. Otherwise, if you look at the number of pores that are present, these type of defects are present throughout the part. Are they critical or not? And that's another big decision. Like, not every pore is critical and not every pore deserves the same level of attention. So we need to identify which are the critical regions in my part. At the same time, also understand, if we want to understand how to avoid getting that defect, we need to understand what formed it in first place. And going towards the SEM or light microscopy tools is really beneficial. So let's look at just that figure 8 section from the whole part. And we can look at, there is a large pore that's present here. There is something present here, and there is something here. But with my coarser resolution image, which allows me to scan the entire HIS exchanger in about an hour, is not able to give me all the answers that I'm looking for, but it's a really fast inspection tool. Now, having identified that is the region that we're interested in imaging higher resolution, we can now image the same part at now higher resolution. It starts revealing more details. You can start seeing the surface a little bit coarser and start revealing smaller size pores which were hidden before. As you start increasing the resolution from 80 microns to 25 to 6 microns, you start seeing you are revealing even more pores, and the surface becomes more clear. And we start seeing this is actually a powder which is sintered onto the surface. Then we can add SEM, and one of the advantages with SEM is you can basically, you're not limited by resolution anymore. You can zoom in anywhere you like on the part, and you can walk around, and you can look at the same part at much higher resolution. You can start looking at the powder parts which are sintered to the surface. And what it allows you to do is now you can add even higher level of details to the imaging. At the same time, try to understand, like, if you are looking at the fuel which is flowing through this part and some of these sintered powders becomes loose, during operation of the aircraft, that can cause a lot of problems. In order to understand how do I get rid of some of this surface roughness, or is this surface roughness going to be of a problem at all? So that again becomes very important for operation of the instrument, because oftentimes just cleaning with different fluids in a static condition may give you a result saying, I don't have any more particles coming out in effluent, so I have cleaned the powder all well. But during operation and vibration, some of these things starts becoming loose. We did SEM, but one of the advantages of SEM is now I can also add chemistry to it. So we looked at the defect, we looked at porosity, we looked at cracks, we looked at surface roughness. We can also measure surface roughness. I'll show you towards the end of presentation. But now I can add chemistry. So I can, since the part is made up of aluminum, silicon, magnesium, I can look at where the aluminum signals are coming from, where the magnesium signals are coming from, where the silicon signal coming from. And if there are any inclusions or impurities, those also will become very, very visible. So if for example, if I had a part from, for example, say Inconel build, which was coming into this powder batch, and that gets included in the part, you'll start seeing signals of Inconel components. In this case, the part was very clean, so we didn't really see any impurities, but you can also start adding that information. Now I can also start looking at the mechanical properties by adding EBSD. So backscatter diffraction imaging start showing you this figure we are seeing is fairly large. It's every image I'm showing you is made from multiple images which are stitched together. So this is the data that's coming in from EBSD, and you can start seeing the grain structure around these parts, and you can start looking at basically different contouring strategies, grain structure in different regions, so directly affects the mechanical behavior of the part. So what we're able to see is the part which is imaged in its entirety for complete inspection and fast inspection. Then we can start looking at saying, this is the problem area, can I see that at higher resolution? So we can just add that tool. I think that can also do collected CT. Every time at high angle, the strain reduces, and basically what happens, the tube starts getting pulled in. With a different print pattern, or something needs to be done to correct its design, either topology optimization or print pattern optimization. Because tube makes a contact with bull, you can start seeing around that the direction of the deviation actually goes from negative down to on how the fluid, if there are any hot spots, yes, during operation coil cooling. Again, these are very, very important pieces of data. Again, all are collected one single part, cutting it open. Except for SEM is where we actually cut open the, but up to this point, negative surface roughness, I'm only going to the external surface roughness aspects, the functional surfaces. Single point of measurement is not a single array to give us the full answer, because if you look at 3 regions which are about 1.5 centimeters, seeing the surface roughness is completely different in these 3 areas. You see the same changes happening on the internal tubes as you do not have a surface roughness. So we have to come up with a technology where not only we capture large enough area to be able to get representative volume, but you also need to understand what type of surface treatment I need to do in order to get to the desired surface roughness. So far in this example, what we have seen is the CT data, which is basically able to capture the part in its entirety and show you all the defects. Your micro CT data, where we are zooming into a part, and at any given point of time, you can only see a small section of the part, but at much greater resolution. I showed you FIBSEM, where we can start looking at SEM, FIBSEM at sub-nanometer resolution imaging and all the way down to, but the volume is of the hundreds of micron cube. So you can do the same analysis in 2D or in 3D and get much richer information compared to just the morphology or defects. You can start adding chemistry to that. You can start adding grain structure or mechanical properties. And then, of course, you can prepare sample for TEM and atom tomography. So these are the resolutions. Of course, on the industrial scale, you would be working mainly on this side. In academic scale, you'll be working mainly on this side. But for additive manufacturing, as it transitions from prototyping to production, it needs to do both. It needs to do the industrial inspection at the same time in order to get the process working right the first time. You also need to do quite a lot of material science. So this entire chain of tools allows you to basically not only get the answer right, but do it very fast with minimum number of builds. So all this information we are able to give them have been able to significantly save the amount of development time that was required to get the part right. And those are the only tools I showed, but ZEISS is one of the fortunate companies which has this entire product line, which can go from nanometer scale to light microscopy, to CT, to very fast industrial CT, CMMs, pretty much entire process chain from industry to research is all captured. And I'm fortunate to have all these tools available in my lab at Oak Ridge. And what we are doing is using these tools to do the correlative analysis. So these tools do talk to each other. So the data that you see is coming from CT can be easily correlated to the data that micro CT is measuring. That can be correlated to the data that any of the microscopes are measuring, electron for light microscope. And similarly, 3D scanner and CMMs. So the idea is just collecting data is not sufficient. Analyzing data in its own island is not sufficient. If you have this data integrated and talk to each other, then you get much quicker and much better answer compared to a single tool that can provide. So having seen one example, let's go a little bit deeper into each of these islands. I'll show you quickly some examples through that. So let's look at how we do the powder analysis. When it comes to powder characterization, oftentimes for additive manufacturing, the size distribution is important, but more important is also shape of the powder, because that's what controls the flowability of the powder, and surface of the powder, because again, that controls the flowability of the powder. So if you look at light scattering or any other indirect measures, they automatically assume the particle shape and gives you size distribution. So they assume powder to be spherical, and based on some spherical assumption, it tells you what is the distribution of the sizes. But if you do directly observe the particle itself using light microscopy or SEM, you can actually go and measure the shape of the particle. Of course, just collecting images is not sufficient. So we have the full workflow where we are taking the images of the powder, automatically segmenting it and converting that into data. And there are multiple characteristics that are available talking about size and shape of the particle, aspect ratio, elongation, and everything else that comes with it. If you add additional level of information now to your powder characterization, so not relying only on the size and shape, but if you want to also understand the chemistry about the particle, so you can use SEM, and SEM gives you that added information. So SEM, of course, can give you extremely high resolution images, so you can see the shape of the powder particles. And the software automatically goes and separates out the particle and categorizes each of the particle based on the size and shape, number of satellites it has, all that stuff. But with SEM, you get that additional advantage. You have with SEM, you can also add EDS. So by adding EDS, now also you can start getting chemical information. So you can look at the powders before, they all look more or less the same. But once you start understanding chemistry, you start finding there is one particle which is not inconel. And based on the histogram, you can go back and find out this is actually aluminum silicon and magnesium. That's basically coming into a powder batch because of the contamination or powder handling or mishandling. So that's the level of information you can start getting very quickly right at the powder, even before the powder goes into a build. So you can think about aluminum powder coming into inconel build. Now you basically pretty much vaporize this material. If the vapors are not able to escape, that becomes a trapped porosity in your part, or that can create instability in your melt pool that can have its own different effect. Vice versa, if we have inconel impurities or tungsten impurities coming into your lower melting material, then those parts might just remain as an inclusion in your final part. And that can often be the crack initiation sites in your final part. So we have an example where we saw in a turbine blade having in an inconel blade, we had tungsten powder, and that was a crack initiation site for those blades. How can you also look at the powder particles or inclusions that come in as a result of powder characterization missing out on that chemistry information? So if all we did was size and shape analysis on the powder and the powder goes into build. So here is an example part built with aluminum silicon 10 magnesium again, built with SLM machine, that's like gear. And very first thing that we did is take a CT image of the gear. So if you take a CT image of the gear, that's what it looks like. If I make everything else transparent and just leave only the inclusions inside. So if you look at, this is the size of the part, about 25 millimeters, about an inch in diameter. I make everything else transparent. So there are very few specks of powder or inclusions present in the whole part. If you were to directly assume the particles exist and just straight away go and cut it, chances of you going and hitting a cross section, which will include these particles, is extremely rare. It's like finding a needle in a haystack. So having that CT image initially helps me to basically pinpoint on saying, yeah, here are the locations. I want to find out what exactly that thing is made of. CT can tell me that it is brighter than aluminum, silicon, magnesium, but it cannot give me a chemical idea on what that powder or what that inclusion actually is. So with CT, we localize and find out where the inclusion is, prepare the sample in that way, and put it in SEM this time again. And what we are able to get is we look at the bulk. That's basically you're seeing aluminum and silicon signal. But at the point of impurity, you see iron, manganese, chromium, and cobalt. Right? And that is your inclusion. And of course, that is your H13 tool steel. And if you start looking at the source of impurity, basically what happened is they had a powder change going from H13 tool steel that was left over from previous batch, and improper cleaning of the printer basically led into this inclusion getting included in the part. Of course, not all inclusions are bad, but if that is of concern to you, then this is the level of analysis that you might require in order to understand where the cracks are getting initiated. If your alloy is crack prone, more likely than not, the chances are pores or inclusions are your crack initiation site. If you want to understand surface of the powder and what happens to the powder as it gets heat affected, so we are now looking at recyclability of the powder. You can also understand, like, as the powder gets heat affected, what actually happens to its surface. Initially, you start off with the powder which looks like this on the surface. Of course, that has a very different flowing characteristics compared to the part which is heat affected, where the powder might retain its shape, but because anything which is agglomerated typically gets sieved out. But if the parts are not getting sieved out and still you have a bad flow characteristics, most likely a powder is heat affected but not agglomerated. And you start looking at the surface, and then you understand why your powder is not flowing very well, even though after sieving, your part is of acceptable range. If you want to do even deeper dive into the powder and understand the internal structure of your powder particle itself, I don't think on an industrial scale that will be needed, but it's an academic exercise. You have tools available called FibSem, where you can go and take a single powder particle and create a nanometer resolution 5 to 10 nanometer resolution 3-dimensional image by serially slicing and taking SEM images. So use focus ion beam to just shave off a small layer and collect images. Gives you extremely high resolution imaging, but I'm not sure if that is going to be of much value on the industrial side, but if that is of interest, the tools are available. What I would recommend is if you're looking at internal porosity of the powder, using a micro CT imaging. So what we are using in this case is a micro CT tool, which not only gives me a full 3-dimensional image of the powder, but I'm able to sample a lot more number of powder particles and get much better statistical answers. So here at any given point of time, we're able to sample about 100,000 particles. It gives you very, very nice statistics. At the same time, it is the only tool which gives you full 3-dimensional detail on the particles. At the same time, also be able to look on the porosity that is present inside the powder particle itself, because this gas porosity from inside the powder particle often stays inside the part as well. Here's an example where we are looking at this gas bubbles inside a small powder particle. And in the final build phase, like I'm showing you the optical section, and we are seeing this perfectly spherical, very small gas bubbles that stay in the part, because as you're melting the part, the rate of solidification is much faster than the escape velocity of the gases, so they remain trapped in your part. If this is of importance to you, then looking at the porosity, source of the porosity is quite critical. Not necessarily all applications will require this level of details, but if needed, the tools are available to basically do this type of analysis. And like I said, a single tool will not be able to give you all the answers, but the idea is if we have a particular defect and you cannot trace the sources of it, then you might require to do some level of investigation. And if that's a source of porosity or crack or part failure is critical enough, then every incoming batch of powder, you might also start nip the problem at the bud is what I'm trying to say. It's like start looking at the powder, and if the powder is of certain characteristics, you can have a pass-fail criteria right at the very first stage, even before the powder goes into the printer, because if that is of critical necessity, we know that it's going to affect your part anyways. So better to stop it at the source. Of course, again, CT, be it CT, SEM, or optical light microscopy, all the images need to be converted into some sort of statistics. So you have software which automatically does this type of analysis for you and gives you actionable intelligence on the part. This is another area which I wanted to talk about is the heat treatment. Let me show you one example. Like this is the work we have done with NIST, and what we are seeing is a build plate that was created using steel, and we measured all the features. Let's plot just two of the features here and look at how they are changing. So on as printed part after depowdering, what we are looking at now is just measuring this part. The part is still on the build plate as built. And you look at the flatness of this contour and cylindricity of the hole that is right in the middle. So if you say part has a tolerance about 50 microns, you say this part is just barely intolerance, about 54 microns and 53 microns is the total deviation. But if you look at the deviation, basically on the edges, you have very flat surfaces. As you go towards the center, you have a part which is going out of spec. If you look at the whole, again, it's not very uniform from bottom to top, from left to right. Again, there are deviations. If you were to remove this part without heat treatment and take it off the build plate, you start seeing completely different answer. Now you have much higher deviation on the edges of the build plate. And what we are also seeing on the whole is, again, the signs were basically where it was contracting before and now expanding. But if you look at the specifications, now the part is 10 times out of spec, while the whole actually gets even better, going from 53 microns to 38 microns. So what we're seeing is basically the part doesn't behave the same way throughout. Even though it was built on the same machine with the same material at the same time, because depending on the heat treatment and the history of thermal history of the part, you get very, very different mechanical behavior. If you were to heat treat the part and remove it from the build plate, again, you start seeing deviation, but the deviation is in control, but again, it's not following any specific direction, especially if you look at the image of the cylinder. So the reason for that is you started off with the part which was built with additive manufacturing, and oftentimes what we end up doing is copy the recipe from conventional manufacturing for heat treatment. So if you look at the conventional material, this is what the microstructure looks like. An exact same material, if you print it with additive manufacturing, the image on the right is of same material. You get very, very different microstructure. And if I were to draw your attention, the scale bar here is 100 microns. This is actually 5 times more magnified image. So your starting grain structure is extremely fine with additive compared to conventional. So if your starting point is very, very different and you have very different, not only grain strike, but very different strain starting point, the same recipes may not work. So you have, what we need to work on as a community is heat treatment procedures which are optimized for AM processes. So copying and pasting might not work each time, and for all the elements, for all the new materials that we're making. The reason for that with the additive manufacturing gets even more complicated is within the same melt pool, not only you have very fine grains, but within the same melt pool, again, you have heterogeneity in the grain structure. So on the edges of the melt pool, you have much larger grains compared to in the middle of the melt pool. So we need tools which can go and measure the grain sizes and optimize the heat treatment. So we have one of those tools called LabDCT. And what LabDCT does is basically measures, along with CT, it also measures the grain boundaries or grain structure in 3D. And the advantages of doing it in 3D compared to any other technique, which basically relies on cutting open the grain to look at the grain structure, along with its location, is when we do analysis like that, you can also perform experimentation on heat treatment. So here is an example. You can perform 4D imaging. So here's an example where we are looking at the traditional CT image on the top of the copper particle sintering. So you can start seeing before heat treatment, after heat treatment, the part actually starts creating necking, and some of the molten part actually starts agglomerating. The image at the bottom is showing exactly same image, but with a different viewpoint. Now we are looking at the grain boundaries or grain structure, and you can start seeing the grain sizes. They change as a result of heat treatment. So you started off with a very different heat treatment procedure, and then you end up with a very different number of grains because some of the grains actually start merging with each other. So you started with 226 grains, end up with 130. So this type of tools basically give you a good handle on how do you want to go about heat treating your part, which is manufactured using your print parameters. You can also perform 4D imaging to understand the mechanical behavior. So you can do compression, tension, torsion, different type of tests along with the heat treatment. So we'll not do the next. There was a poll question. Let's do there are 2 additional poll questions that are coming one after another. So if I can get you to answer those 2 questions, that helps me in discussion on the next slide. So let's give about 30 seconds on this question, and immediately following this, we'll have one more question. And we're almost near the end of the presentation now. And let's go to question number 3. Jenna? Perfect. So let's get on with the presentation again. So what we typically look for when it comes to defects is, of course, the porosity, delamination, and depowdering. So I'll focus on just a couple of those things. Based on your answers, I can see almost everybody prints coupons with their builds. So one of the things that everybody does is, of course, Archimedes density, but at the same time, optical cross-sectioning. Take cross-section and measure it under optical microscope. So these are the two steps that are taken with each other. What we suggest is basically adding one more step in the middle, which is basically very fast CT scan. And the reason why I recommend that with the coupon analysis is by doing fast CT scans, you can actually look throughout the part. You may not be able to see all the pores, the fine pores which optical tomography can show you, optical imaging can show you. But what it allows you to do is get unbiased answers. So if you were to just take a cross section, if you look at the coupon at the top, if the cross sections were to come from the bottom or sit through the middle to the top, you'll get 3 different answers, and each one gives you extremely biased answer on saying very bad, very good to middling. So adding along with the tomography, if you add optical CT imaging, optical imaging, it tells you the sources of bias if there is any present, so you know how to deal with that data differently. And this sounds trivial, but oftentimes we start seeing the parts which are considered to be made of very good parameters. If you were to actually go and look at the entire coupon, it starts showing completely different answers. Of course, it's not that common, but if it happens, it can be of high economic impact. And here's another example on the depowdering side. I wanted to show you. This is the gear part that is built and cleaned. So this part was cleaned to the best of its ability, and then it was imaged using CT. So what we're looking at is the imaging of the entire part. And then as you start focusing on to a certain area of the part, we start seeing there is a powder patch which is sitting, and we're not really sure what is actually causing that part. So you can image the same without cutting open the part, just zoom in right at that while the part is still sitting inside the instrument. You say, yeah, I want to look at that region at higher resolution. It's like a Google map. You could pretty much zoom in and it starts showing you more details at that area. And as we start looking at the details, in the first image where we saw the whole gear, we could see this part. It looks like a blob. I know that should not exist. We start seeing some of the higher density material here. And using high resolution imaging, you can start looking at whether the powder was completely cleaned up or not. And here we find basically this is the agglomerated powder, which is sitting in the corner. Heat affected, slightly agglomerated powder. So again, cleaning or depowdering, if it is an issue, then these are the type of images that might be of use. And the last part is basically as we start creating more and more complex materials with additive manufacturing, measuring those parts become extremely challenging. So how do you measure these free-form surfaces or extremely complex geometry like lattice using traditional methods? In that case, traditional methods may not be applicable. So what we are doing is we have developed this metrology capable CT instruments, which allows you to go and take the CT image of the part and be able to measure internal, external features, similar to the examples I showed you in the heat exchanger. Second thing that it also shows you is basically if there are any surfaces which are either powder patch sitting there or surfaces themselves are very, very rough. And you can use CT again to go and measure surface roughness. And like I promised before, we can use CT for measuring surface roughness. So how do we know that CT measured surface roughness actually compares well to the traditional measurement and where it can and cannot be used? So if you were to basically look at just the flat plate, the test plate that we built, and measure it using Versa, which is our X-ray CT, that's the image coming in from the CT, and that's the image coming from traditional confocal microscopy. So this is a laser confocal microscopy comparing same identical region with X-ray microscopy. The results are in very good agreement in as-built part. How about when the surface roughness gets very, very fine? Can CT still pick it up? So now you look at this part, which is now after polishing. Now this part is bead blasted and we measure it again. And of course, the surface is getting smoother, and CT is still able to capture very, very small deviations on the surface. So it's a good surface analysis tool if the material permits it. How do we use it in the real life? So here is fluid manifold. That was hydraulic manifold that is used in the earth moving equipment. And we can see an as-built part on this critical juncture where we get the maximum impact on the flow, what the surfaces look like. You can go and measure them, and then you can find out a way of doing different type of slurry flow media and optimize the flow and be able to get the surface roughnesses. And you can continuously monitor it. And once you get the surface roughness of certain desired quality, then you can basically understand how to treat more of the sample at the industrial scale. So CT is one of those tools which can basically, where a traditional probe cannot touch or a light cannot reach, in that case, CT would be a very good tool to use for measuring surface roughness. And that was the last example. So these are all the tools that are present in order to basically look at the additive manufacturing in a fully integrated manner. And one of the things that I want to highlight is just having instruments alone is not sufficient. You also need the instrument to be able to talk to each other in order to basically do the full quality analysis. With that, I'll take any questions.
All right, thank you, Pradeep. Now into the Q&A session. If you do have a question for our presenter and you haven't done so already, please type it into the chat box. I do have a question here to get started with. So what in-process sensors are you using? That came in the very beginning of the presentation.
So in-process sensors, ZEISS is working with powder bed monitoring. So we have optical sensors, and then there are a few other sensors which are in development. The sensor technology, the way we see it, is slightly different compared to other sensing technologies. So what we are expert at, what ZEISS is expert at, is imaging. So with in-situ monitoring, what we are seeing with optical sensor especially is the quality of the images that are generated. They require, they may not be able to isolate false positive very quickly. And what requires improvement, especially on that side, is a really different way of collecting the images. And ZEISS has probably about 170 years history working with optical imaging, and that's what our sensor excels at. Of course, at the back end, there's artificial intelligence. So one that is released is the optical sensing. There are a couple of other technologies that we are working on, which will come out in next few years.
Okay, thank you. Let's see. So we have another one that came in here. Is the powder bed inspection integrated with existing equipment like EOS, SLM, 3D systems?
You should see some announcement coming in Form Next. But we are, the idea is to be able to integrate this and try to close the loop if possible. So that's one of the reasons why these things are being deployed through OEMs rather than just buy directly. So this, you will start seeing some of the ZEISS tools in selected OEMs.
Okay. All right, here's another one. It appears outside AM service providers can access your lab for analysis, correct? Who is the best point of contact for quoting? Can you just contact you at your email address or the additive@zeiss.com?
You can basically contact me or additive@zeiss.com. Both the emails would work, and we have nationwide 6 different facilities which do measurement, and all the labs are fully equipped. And recently we also opened up a lab in Michigan, which has even more equipment, which can give you very rapid results. So please write to me, and either I can help you or I can point you to the right person in your region.
Okay, great. All right, so wait a minute or two. I don't see any more questions coming in. If any more do come in, I will ask them.
And if you have questions after the presentation, note down my email or additive@zeiss.com. And please send, we are always open to basically, we are always open to any new projects. The lab at Oak Ridge is dedicated for research. So if you have any research questions, contact us directly. And if you need a product demo, or if you have a particular part that needs to be measured, again, contact me and I'll guide you to right place.
All right. Thank you very much. So that will wrap up today's TRX webinar series. I would like to once again thank Pradeep. If you have further questions for the presenter, reach out to him directly. His contact information is on the TRX webinar series screen. Excuse me, there will be a post-webinar survey going out to all those who participated. We do really appreciate the time that you take to make feedback so we may continue to improve and strengthen the additive community. And a reminder, if you think that you or your organization will be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation. Reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org. Thank you very much and have a great day.
Thank you.